Now that you said that he's revising his
You're right. I'm going to tell you a joke after this.
What, now tokens are continuous?
What?
Now tokens are continuous?
Oh god, yeah. No, it's bad. Yeah, let's start.
Okay, so thanks for attending the last session of the workshop. And actually, before I talk about Max, I'd like to have a round of applause for Andre, who did a lot of the work for this workshop. So yeah, thanks, Andre, and thanks everybody for coming. And if you have any comments, you can email or contact any of us any way you like. So we're very happy to have Max Simchowitz for the last talk. It's actually kind of astonishing to think that he's just about to start his first faculty position, because all of us have basically known him since he was starting his PhD. He's done so much good work across his PhD and his postdoc that, yeah, we could have just been tricked to think that he's been faculty all these years. And there are a lot of interesting things I could say about him. And for those of you in the program, you already know that he's been very vibrant in the community. So we're also very fortunate to have him in all the things he's organizing. But one thing I want to say about him, which is directly related to the talk, is that he made kind of a very brave decision that he did a lot of mathematical work as the focus of his PhD. And then he very deliberately chose to do robotics. So he was at Berkeley, and then he chose to do robotics work at MIT and get his feet wet on a lot of different skills. And I think for all of us that follow his career, it'll be very interesting to see what he does in his new faculty position. So we're looking forward to the last talk and have a good time.
Wow, thank you for the too kind introduction. That's really nice. It means a lot to me. So thanks for braving till the end of the workshop and being here on a Friday. I'm going to try to keep this talk a little bit chill because we're all tired. Maybe we all want to go home. And kind of the point of departure is that lots of us have been seeing talks around LLMs, maybe binary classification, but things that happen in the discrete world. And because I've had the fortune to spend time with a lot of roboticists, I think about what happens in sort of continuous spaces. And I want to explain how things might be a little bit different when we're in a continuous space versus a discrete space. So as a point of departure, I'm going to focus the majority of the talk on this problem, robotic behavior cloning. So here's a video from my industry partners at TRI. So in robotic behavior cloning, you have a human demonstrator. They're operating what's called a teleoperation machine, providing demonstrations to a robot. The robot's taking in the demonstrations and then learning to predict actions given measurements, say visual observations or tactile observations, in order to learn skills. And a variety of skills can be learned in this way. Here you're seeing egg beating, but you can also have other sorts of practical skills learned through imitation. So robot behavior cloning is rapidly becoming kind of a building block for many modern robot learning architectures and paradigms. And this is a list that I had when I was giving this in a job talk, and it's already become antiquated because there've been a new range of robot startups built on sort of large-scale robot imitation from demonstration. And even if you don't really care too much about robots, this is not a robot or control conference, but you care about sort of broad AI, broadly construed, robot learning is also kind of giving way to these open visual language and action models that try to combine video prediction, text prediction, language, and sort of grounded real-world understanding. And so kind of, I think the central thing here is that we're predicting not just, say, discrete tokens like objects of mathematical reasoning, but what I'm going to call continuous tokens. Please forgive me for my bad nomenclature, but sort of continuous objects in continuous valued spaces. Okay. So to formalize this, we're going to view behavior cloning as operating in a nonlinear dynamical system. I'm going to do my best to keep control theory super light for this talk. So here we're going to use states to represent the state of the object and the robot. So that's just like a world state. And inputs are going to denote robot action. So we're going to follow the control convention where input is the letter U. And you can call these continuous tokens. Again, forgive me. If you were a robot person, you'd shout at me because, in fact, one of the best things about behavior cloning is that you don't need a pure Lagrangian state, that you just get a visual observation. But to do the math, we're going to assume access to state, so we're not in terrible POMDP land. Okay. So a couple themes in the talk. We're going to talk about how in behavior cloning things go out of distribution. But interestingly, how this differs from the kind of out of distribution effects that we might see when we have discrete tokens. We're also going to spend some time talking about what we can do about it and how some of these ideas appear and trickle into and might inform some things that we see in applications. Okay. So let me kind of just be a bit more specific. The template for behavior cloning is as follows. We take n expert demonstrations, right? So trajectories of states as well as the inputs that generated the states. And then our goal is to train a predictive model, which we call a policy, which predicts actions given states, right? Trying to fit the expert data that we get. And ideally, the predictive model would give us trajectories that look something like this, that roughly approximate what we see from our expert. So in particular, we're doing pure learning from demonstration. There are many ways, pure supervised learning from demonstration. There are many ways to imitate demonstration data, but here we're not using anything like a reward model. We're just trying to fit the conditional distribution of expert data. This, of course, has its pitfalls, but it sort of is kind of a big part of the robot learning pipeline, and so we're going to focus on this itself. One of the big advances in behavior cloning, arguably the reason that you've seen a surge in behavior cloning efforts, has been the use of generative models, not to produce data, but actually as parameterizing the supervised learner. So to fit the conditional distribution of actions giving states using something like a generative model. One popular class of such models are diffusion models, because we know that they can represent very general kinds of distributions over images. But of course, transformers are also more or less as effective for these tasks as well. So what's kind of a reason why you might want a general generative model instead of just doing point estimates of actions? Well, in many cases, human beings might have multiple strategies for solving the same task. So as a stylized example, here we have an obstacle, and I can choose to go left around the obstacle, or I can choose to go right around the obstacle. And a generative model can capture sort of both modes in our data. So we call this multimodal, not in the sense that data has different modalities, but in the sense that we have different modes, and generative models can fit this. So there are a couple hypotheses why diffusion models might be useful. And I think the natural one we'd call in sort of learning theory realizability, that we have expert data, the expert data is super complicated, and only a generative model is rich enough to fit the diversity in our expert data. But I'm actually going to suggest that there's a tweak on this hypothesis that's probably a little bit more accurate. So an example of why you'd want realizability is because if you try to average between the two modes, you'd collapse, you'd go right through the obstacle, and then that would be a bad idea, right? So you want to actually represent these bifurcations. But my proposed modification of this hypothesis is actually that diffusion models can have different out of distribution or inductive biases. And maybe the reason we want rich models isn't for them fitting in distribution data, but them doing the correct thing out of distribution. So maybe a way to visualize this is to say, imagine that my data, I didn't have data in between the center, right? I just had these two separated modes. Then a deterministic model could fit my data, right? My model can fit something over here. It can be garbage in this nether region, and it can fit the data here. But nevertheless, a diffusion model might be able to fit the data out of distribution, sort of interpolate the data in ways that a pointwise predictor can't, right? So the first hypothesis is about fitting our expert data, and the second one is about fitting things we don't see in our data set. And I'm going to claim that hypothesis 2 is really what's going on. So let's make things a little bit formal. This is Simon's. I have to do a little bit of theory, but I try to keep it light. As a preliminary, I'm going to define the epsilon relaxed TV distance. It's not really a distance because it can be 0 even if two things are not exactly the same. So here what we do is we look at two distributions P and Q. They specify random variables in the same norm space. And we look at the probability that these random variables differ by more than epsilon. Of course, when you give me two random variables, I need to specify their joint distribution. So I do the optimal transport thing where I specify the most favorable joint distribution or coupling, which gives me this over here. Notice that if epsilon is 0, this is just the probability that under the best coupling, these two things are equal if you have a norm space. And in particular, that reduces to the classical total variation distance that many of us might be familiar with. The reason we like epsilon TV, and I'll show you exactly why you might want this on the next slide, is that it's a bit more natural than regular total variation distance for continuous valued random variables. Because if you perturb two variables by like a small metric amount, right, you want a distance that doesn't sort of change discontinuously, and TV can change like that. And of course, lots of us are familiar with things like Wasserstein, which are other kinds of forms of optimal transport distances that are metric aware. But for the purposes of today's arguments, the epsilon TV is just more convenient to work with. So we're going to stick with it. Okay. So training error, we get trajectories that come from our expert, right? They're going to be in the blue. And what we're going to assume that we can make small is something that we can get from supervised learning. So this notion of training error is as follows. It says, look at all time steps. Look at the distribution of states visited by the expert on those time steps. And we're going to assume that we can make the TV between these states, the actions the expert would take at that state, and our learned policy pi hat small, right? So this is just on the distribution of expert states. And as a consequence of being in distribution of our training data, we can actually show that for DDPMs with, say, score functions of bounded Rademacher complexity, one can make this small. Just as a note of caution, this is why we can't make epsilon 0. Imagine your data actually lies exactly on a data manifold. Then to get epsilon equals 0, strict TV, you have to also make predictions that are exactly on that data manifold. And this is hard in general, right? So that's why we need this little bit of epsilon as form of our relaxation. All right, so our test error is as follows. Now we've trained our policy. Now we roll it out in the dynamical system up here, and we choose actions according to the test policy. And the thing that we want is, for simplicity, let's say, we want the states that our expert generates and the states that our test policy generates to be close in distribution. So here, law, I'm just using to mean the distribution of these two states. And we want these to be close. And again, we're going to choose the epsilon TV. So our goal is, something like this, right? To have our trajectories that we roll out look close, generate states that are close to what the expert gave us. And kind of more formally, this is just to say that, we want our test error to be controlled by our training error, times factors that depend nicely on problem parameters, in particular, are polynomial in the horizon of the problem, right? So that's kind of the overall template we want. We know we can do supervised learning. What does that mean when we roll things out? So let me explain how distribution shift arises, and I can just illustrate this with deterministic policies. So in deterministic policies, let's just focus on making the trajectory distance small and over random initial conditions. So here's my expert, here's my learner, and everything starts off fine because my initial states are always in distribution, so I make a small error here, but it's not so bad. But as I continue to roll out the policy, the errors can accumulate, and they can accumulate exponentially in the problem horizon. This can get pretty bad. But there's kind of a more interesting challenge, which is that even if I've encountered just a little bit of error over here, I'm now out of distribution because it may be the case that none of my expert states look like the one over here, and I need some way of moving myself back onto the distribution so that I can use the training data to learn effectively. So let me give a contrast to what you might see in discrete behavior cloning. In discrete behavior cloning, let's say we have our tokens going this way, and most of the time, if I have good supervised learning error, I get the first token right. But sometimes I make a small error. And again, most of the time I get this token right, but I make a small error and so on and so forth. So indeed, my errors do accumulate, but these are probabilistic mistakes. So they can accumulate at most linearly in the problem horizon by a union bound, right? So this exponential compounding error that we see in continuous tokens, we can't really see in discrete token land. And in fact, Dylan Foster's got some amazing work showing that you can get even better than this depending on sort of how you structure your function class using the log loss, which I think is very cool. So maybe another way to think about this here is the problem is that mistakes are not probabilistic. They're not these 0-1 things. They're metric, right? We're always making a little bit of error in the metric space, and that's going to kind of bite us. So maybe you might say, okay, Max, but this is just a problem of control theory. You're looking at pathological control systems. Stop trying to solve Navier-Stokes. What if you just make the dynamics super easy? So let me suggest an easy form of dynamical systems that might be illustrative, right? These are going to be called contractive. You can also call them Lipschitz. So I'm going to call a system alpha beta contractive if the difference in the dynamical function differs by between states x prime u and inputs u prime and xu differs by alpha times the distance between x and x prime plus beta times u and u prime. And I'll use contractive specifically to refer to the situation where alpha is strictly less than 1, meaning that sort of when you take the same input at states, at two different states, the next state is getting closer to them, right? So they're contracting. So it's very easy to show with a recursion that if you have contractive dynamics and you have two sequences that start at the same initial state and alpha is less than 1, then the difference between these trajectories is controlled by the difference between these states, right? This is just kind of a direct computation. So you might think, okay, exponential compounding error should not happen in contractive systems, right? This is actually a special case of stability, which is a more common condition in control theory that we look at. So let me give you an example. Here's a contractive system. It's scalar dynamics, x and u are scalars, and it's contractive with alpha is 0.9, as you can just see directly from the dynamics, right? So I'm going to assume that the expert policy does nothing. It's always pi star 0, and my initial condition is always 0. So my expert data is always identically 0. And now I'm going to give you kind of like a resisting oracle, a bad learner for this data, and it looks like this. I'm going to call it pi hat bad. So what pi hat bad does is it's 0.15x plus epsilon. Maybe you can see where I'm going with this. On all the training data, x is 0, and so 0.15x goes to 0, and this is 0, and it's always epsilon apart. But what happens when I actually deploy this policy? Well, if I look at what we call the closed loop dynamics, so I plug pi hat into our dynamics, this becomes 1.05x plus epsilon, and you can see this quantity is strictly greater than 1. And what that means is that if you run through the recursion, you can actually show that the magnitude of the states under this bad policy grows exponentially in the problem horizon. Right? So really the culprit is this, right? It's not that the dynamics are bad, nor is it really that the extrapolation behavior is super erratic, right? This isn't a massive Lipschitz constant. It's not something that's not smooth. But it's really that the feedback between the policy and the environment, this sort of weird inductive bias that this policy happens to learn, can be quite catastrophic. And you might think that this is fabricated, but in fact, in some wonderful work led by Adam Block and Cyril Zhang at Microsoft Research, they show that depending on how you train your models, you can have these really bad inductive biases that lead to what we call butterfly effects, leading to pretty catastrophic behavior cloning behavior downstream. Okay. And of course, you might say to me, okay, well, if you just had better data, you're giving me terrible data. It's just 0 all the time. And indeed, that is the case. You can prove that with better data coverage, this doesn't show up. But we don't get to control what our expert shows us. We need to make do with the data that we have, right? But you would be correct that with better data coverage, this isn't so much of an issue. So in fact, what we can show is that a problem of this form is actually unavoidable in certain systems. So if we look at a condition that's slightly weaker than contractivity, one that's called stability or incremental stability, we can show that essentially exponential compounding error is unavoidable in the worst case without other conditions under data coverage, even if the system is stable. And this is somewhat surprising. And so better dynamics naively doesn't fix this problem. And in fact, we need either better data, or maybe we need to use knowledge of the dynamics, right? Because maybe if I know that the dynamics look like this, I might know that this is a pretty dangerous inductive bias to have, and I might try to avoid myself from learning policies like this. So there might be some way to regularize this out. But actually, I'm going to talk about how we beat compounding error. And it turns out I lied to you. So I said that if the system is stable, you're out of luck without additional assumptions. But actually, if the system is contractive, which is this condition over here, you can imitate without exponentially compounding error. You don't need exponentially compounding error, and I'm going to explain why this is the case. And then the second thing that makes this interesting is contractive systems are pretty rare in actual applications, but it turns out that if you know the dynamics, there is a reduction to learning in contractive systems where this alpha term actually goes to 0. And this uses ideas from layered control theory where you imitate not just actions, but actually control policies. But because this isn't a control workshop, I'm not going to go into that side. I'm really just going to focus on theorem 1 over here. Okay. So this is going to be the focus of this part of the talk. So I wanted to motivate how we go about this. I want to suggest a different inductive bias that's not so bad. So we'll remember our bad example here, this contractive system. But I'm going to define a not so bad learner, which uses the same, which kind of takes the previous inductive bias, but then Bernoullifies it, right? So it makes this a 0-1 random variable rather than a metric error. So the intuition here is that, if we believe that discrete token error is not so bad, continuous token error is bad, maybe we can get away with this. And indeed, what you can show is, in fact, this policy doesn't do so badly, right? So it's going to stay within about epsilon. The state magnitude stays around with epsilon with some probability order 1 minus t epsilon. So the way to see this is that, sometime you make this Bernoulli thing kicks off, right? You make a huge mistake, but most of the time you make only a small mistake. And again, sometimes you make a huge mistake, but most of the time you only make a small mistake. And because the system is contractive, sort of these mistakes kind of saturate over here. And then this gets eaten up in your union bound, right? So this policy is actually not so bad. I think this is right. So what we've done here is we've just said, imagine a policy which makes sort of discrete token errors or probabilistic errors rather than metric errors, and this thing is not terrible. And this is actually a motivation for why we might want generative models, because of course, to represent a policy that makes errors like this, you actually have to be predicting a distribution over actions as opposed to a mean. Indeed, if we just took the expectation of this policy, we replaced it with its expectation over its own randomness, if x isn't too big, we actually get back the original bad policy, right, the 0.15x, which is the policy that leads to exponential error. Okay. So let's formalize the condition that this nice inductive bias has, that this policy with a nice inductive bias has. We're going to call it total variation continuity. And it's just the following very simple condition. It says that if I perturb a state by some amount, then the total variation distance between the policy pi x and pi x prime differs by just that amount. Notice this is strict total variation distance, exact TV, because that's also what we would see in a discrete setting. Right, so as an example, the not so bad policy is total variation continuous, right? Because when you perturb a Bernoulli, perturb the mean of a Bernoulli, then the TV changes by that perturbation. But of course, the bad policy is not total variation continuous because the bad policy is always a delta spike that is changing as you change x. Right, so that's this condition. Okay, so let's maybe a pictorial interpretation of what TVC is. So TVC, if you saw Zico's talk, I think in the last workshop, it's basically the opposite of mode collapse, right? So TVC interpolation between these two modes would be switching from this mode over here, and then probabilistically switching between one and the other as you move towards the mode on the right, right? Whereas non-TVC interpolation would be trying to average them in the metric space, going through and colliding the obstacle. So TVC is like, you can interpret this as opposite of mode collapse. And what we're going to show is that actually TVC policies have low execution error. They don't have big rollout error. So let's just recall the problem definition. We're given our expert trajectories, right? And we know how to fit the training data on the distribution of the expert. Let's look at the test error. So the test error comes by rolling out our learn policy, and we're trying to fit the distribution of our states from this policy to the distribution of the expert states. And again, our goal is to bound the test error by something in terms of the train error. So it turns out we can do just this, and I'll just kind of sketch why this is the case. So if pi hat is TVC and the system is contractive, here I'm just parameterizing contractivity in this way. So it's close to 1, but it can be close to 1, but bounded away from 1 by some positive constant c. Then we can show that the test error is actually directly bounded by the training error, appropriately scaled by this contractivity constant, times something that scales linearly in the problem horizon and also linearly in the total variation continuity parameter. So I'll just sketch the proof pictorially, what's going on here. It's very similar to the example we saw in a couple slides back. So some of the time I make an error, but because of total variation continuity, I can kind of say that what happens over here is pretty close to what would have happened at any state nearby it. And in particular, I can consider what would have happened if I hadn't made any mistake at all. So I can look at what would have happened exactly at this true state. Now I can sample an action from this true state. And because this true state is in distribution, those actions are going to be close to the expert actions. Now, of course, I don't get to act from this true state. I actually take an action from the red. But nevertheless, you know, things stay pretty close by. And again, I can couple the red back to this state and so on and so forth. And using the contractivity of the dynamics, you can show that the error doesn't compound. Right? So the idea is that with TVC, you can always change measure directly back to the expert distribution so that you can get imitation. So in some sense, just to recap, so far we've shown that distributionship can be bad when you have continuous states, but TVC with contractive dynamics lets us get around the issue. And it's a pretty simple proof. But you know, this is a great inductive bias, but why should a learned model ever be TVC, right? That's a lot to ask, right? I just told you an inductive bias I'd like my neural network to have, but I don't have any control over what my neural network does. So what I'm going to show you is a technique to ensure total variation continuity in a way that doesn't sort of ruin things. And I call it replica noising after the idea of a replica pair in stat physics. I'll explain where it comes from. Maybe the stat physics people can shout at me because it's a terrible misnomer, but we called it replica noising. So let me first give you an elementary observation about how to get TVC, and it comes from noising. This is an observation that's known. In fact, one of Andre's students, Elon with Jeremy, has shown versions of this in the past. And the lemma is as follows. So let's take a policy pi hat mapping x to distributions over actions, and define a smooth policy by precomposing this with just a Gaussian kernel, right? So taking x, adding Gaussian noise to it, and putting it into the policy. Then you can show that this new policy is 1/2 sigma TVC. And because it's Simon's, I thought I'd go through the proof. So the first step is data processing inequality. So if we're always precomposing with a probability kernel, the TV between policies evaluated at different points is at most the TV between the Gaussians that we use at those 2 different points. Then I can use the famous Pinsker's inequality, write this in terms of KLs. And if you've taken a stats class, you can compute this and you get exactly the total variation continuity. So this is a very simple observation. Nothing new here. This is sort of things that people know, nothing special. It also might be a terrible idea. You might not actually want to do this out of the box. So again, here's my bad data manifold picture. When you add noise to your data, it'll start to go off the training manifold. So if I ever try to evaluate this policy on in-manifold data, I'm going to now be evaluating at points that have sort of an orthogonal component. And I might have never seen this, and so my neural net might generalize very badly to the noise data. So replica noising is a very simple way of dealing with this, but it has this very nice theoretical property that I'm going to explain. So what we do is we simply train the model to condition on the same sorts of noise that we use to deploy it at test time. So when we take our samples from our expert, we train our policy with noise on the states to predict actions given noise states, and then we deploy with the same noise. So very informally, one way you could think of this is just populating the data manifold with noise states, but actually something cooler happens. So let me kind of explain how you can represent a policy trained in this way. So suppose that our training was perfect. Suppose that this step exactly fits the conditional distribution over the training data. Okay, so what goes on? Well, you can actually write the policy we would learn as the composition of pi star with a deconvolution, with the property that says, okay, given a state that I see, treat that as a noisy state. What was the original state that led to this noisy state, right? This is a deconvolution. And then the way you can view this policy we actually deploy as doing a noising plus a deconvolution. So first we take our state, we noise it with some random variable, and then we deconvolve again. Okay, and I'm going to call this operation, which is a mapping from states to distributions over states, the replica kernel. It's what we call a probability kernel. It maps a state to a conditional distribution over states. So here's kind of a visual, right? You might have some state X, you add noise to it, and then the replica kernel is sort of sampling from the states that could have also been noise to that same purple state, right? That's all it's doing, is thinking it's the conditional distribution of where these states could have come from. And here it is again on sort of this bifurcation data and so on and so forth. But there's actually a very nice property, which is that if you draw the original state from the law of the training data, and you draw this new state X prime from this replica kernel, it turns out that these states are actually identically distributed, right? They're exchangeable pairs, or in stat physics, we call them often replica pairs, hence the name. And this property is kind of nice because it means that sort of at a distribution level, adding noise in this way is actually unbiased. And in fact, with perfect training, you can show that indeed, you're going to be learning something that sort of preserves the distribution over actions in a kind of unbiased way. But just preserving the raw distribution over actions doesn't really help you too much because, you know, if you take the right action, but at the wrong state, that's pretty bad. So there's a second property, and it comes from this idea of Bayesian concentration, which is that you can show that because both of these states kind of are jointly distributed with the same state X tilde as being like X plus noise, you can show that both states are pretty close together as well with high probability. In particular, the distance between the states X and X prime behaves like the distance, the norm of like sigma times W, which is the noise vector. So these states are actually close together. So the mental image here is you're moving to a state that's close together. And essentially what this allows you to do with a little bit of a more complicated kind of coupling argument is show that noising in this way leads to unbiasedness at a distributional level that preserves the distribution of the states that you imitate and indeed lets you imitate the entire trajectory. So this is the kind of key idea. Importantly, for this argument to make sense, it requires that you're modeling distributions, that you're computing a replica kernel, not a conditional expectation of something given noise, but really a conditional distribution of something given noise. And this would only work if you do noising in something that can model conditional probability distributions, not just conditional means. So the theorem maybe doesn't matter as much the specific details, but by sufficiently tuning up sigma, you get something where indeed you can control the test error by the training error exactly what you wanted. In particular, we're not assuming anything that's learned by the model. We're not assuming a TVC inductive bias. We're enforcing it by our algorithmic choices. There is a slight degradation of rates, but don't worry about that. Last kind of interesting point is that the noising introduces a possibility of mode swapping. So you might add noise here. When you deconvolve it, you go to a different mode, but nevertheless, the replica property ensures that the marginal distribution over states at every time step is preserved, and so imitation works out. So maybe just to recap, what did we do? We showed that clever smoothing with noise induces TVC. TVC converts this metric error into discrete token error, and imitation with discrete token error is easy, right? So without the actual details of the proof that Adam Block is still mad at me for because the proof's very ugly, but this should be like the conceptual workflow in your mind, that like we want to use these ideas to get back to the discrete case that's a little bit more benign and easy for us to deal with. Okay, so far we've shown that we can imitate without exponentially compounding error in contractive systems, and we've shown how to algorithmically enforce a TVC inductive bias. And actually to induce this kind of contractivity, we need a bit of control theory to reduce to this case, but of course I skipped over that. But there's actually an open question, and one that we're spending a lot of time thinking about right now with my collaborators, which is, if you didn't do any of this external noising, these noising tricks that we need for our theorems, what are these inductive biases of diffusion models and conditional diffusion models? And it actually, we've got some forthcoming work showing that sort of, in practice, diffusion models are not just more expressive for fitting the distributions that we give them, but actually can interpolate the data in more expressive ways. So they learn these things that we are kind of figuring out. We're calling them sort of like improper flows out of the distribution of the data. And this actually gives it more sort of OD power to kind of give you these nice forms of extrapolation that you might want from sort of continuous token data. Cool. There's a simulation study, but yes.
But do you need this like a diffusion model to learn sort of some combinatorial distribution in which parts of this like have not been covered? Like somehow here you go left, right, and there's like an exponential number of possibilities, and presumably you don't believe your data is going to cover all of these exponential.
This is so actually a lot of these toy experiments are just like you have left and right, and you have no data here, and different choices in the architecture will lead to doing different things in between here. But what we show is that some natural choices will choose to switch rather than will choose to make the switch rather than try to average. So even without a combinatorial number of things. Like imagine just 2 delta spikes. We show that even with 2 delta spikes, diffusion models might do interesting, conditional diffusion models might do interesting things. Makes sense. I'm going to skip these plots because nobody here does robots, so you might not care. But I'm going to go to applications. Yes, Matush.
Conditions and things like that.
It's too forthcoming for me to feel comfortable with. I could check with my collaborators and I can talk to you offline. But in the YouTube film Simon's talk, we'll talk offline. But here I don't think I should do it. It's okay. I will say this. I'll say this. I'll say that diffusion models sort of are the reverse process of a certain class of noising processes, right? Forward processes, and these typically in our diffusion models are relatively restrictive, right? They're kind of linear. They can be described by linear interpolants. But what we're suggesting, kind of very informally, is that there are other forward processes that are not described by the things we use to train diffusion models, and diffusion models might be learning to do the reverse of these things instead. Okay. We might have to edit at the sound of this. I'll talk to you in post. Yes.
Repeat like what's the final algorithm? Like you
Oh.
add noise to state and predict
Yeah.
from the
Exactly. So the simple version of the final algorithm without this control theory reduction and layered control is just when you train your diffusion model, you train your a conditional diffusion model to predict actions given state plus noise. And when you deploy your policy by taking the state that you see, adding noise to it and deploying. That's all it is. Yeah. It's pretty, that's all that's going on. Cool. Yes.
Just out of curiosity, I'm sorry. Let me ask you a
No.
control question. Do you need continuity? Can you get away with ISS?
No, so the lower bound is for ISS. The exponential lower bound is for ISS if you don't know the dynamics. Yeah. The lower bound is for ISS if you don't know the dynamics. If you do know the dynamics, then you can reduce to contractivity. That's the idea. Yeah. And we can talk about this. Yes.
Implicit bias that you just told Matt about due to like the conditional generation.
I'm not talking about, and I'm not talking anymore about this because it's forthcoming, and I really want to respect my collaborators' privacy. I'm sorry, we can talk offline, but it's going to be videoed, so I shouldn't. Yes.
So somehow, like the large sigma only helps you in the bound. Is the only thing that like a large sigma harms you with is how good it can you fit the distribution, like the denoiser?
Yeah. So actually, so the sigmas kind of has to be tuned to be kind of moderate. So the large sigma, this is not exactly unbiased because what you're doing is you're kind of taking the action here, but over here. So when you have a little bit of sigma, it's gonna take some time for the system to like contract back to the new mode. So the sigma actually harms you because you're switching the mode and you need to choose the action that sort of is correct for that mode, if that makes sense.
Where does that appear, I guess, like in the bound somehow?
That,
Like, where does a big sigma harm you?
The big sigma is, okay, so the big sigma, the bound probably looks more like a 1 over sigma times something plus a sigma times something, and then you have to trade it off. I think it's that, yeah, so there'll be something which is like a plus sigma, and then there'll be something like an epsilon over sigma, and then you'll have to trade it off. I have to remember exactly where it is. But you should think of this bound as being plus sigma, but then, or sorry, no, the reason is that it's like a test error plus sigma. So you need sigma to be on the same order as the test error. And yeah, so actually I think the way I've parameterized it, this should be sigma equals epsilon. And then the test error is like epsilon train plus is, if you made this epsilon, you make this root epsilon plus sigma. That's how it works. So it's the amount, it's the magnitude of the error you make, but not the probability of error.
But I mean, okay, even the oracle somehow becomes less believable the larger sigma.
Actually, no, the oracle is easier the larger sigma because the score functions are smoother.
But you need to, okay, but
the oracle is easier for bigger sigma, but it's, yeah.
I mean, I guess there should be some kind of intermediate range where you're just adding like enough noise that finding the pre-images is somehow not easy. Like the posterior is sort of not like concentrated on one bit, and it's not like easy to find it. But on the other hand, it's also not completely diffused, so you're not just sampling something uniform.
So you're saying there should be just some fixed sigma for which you do this? It depends because we're not making any regularity assumptions on the expert data distribution. So if you made smoothness assumptions on the expert data distribution, then I totally believe you that you'd just be able to go to 1. Or if you made separation or margin assumptions, it would work. We're making no assumptions, so we need to trade it off. But that's a great question. Yeah. Just to conclude, I think we've all had a lot of theory today, so I'm just going to talk about how these ideas show up in applications. Obligatory slide. So, you know, lots of these discrete token models, right? Like things like GPT, where you predict text or you predict reasoning symbols. But there's a lot of excitement around things like video prediction, climate prediction, AI for science, where now you're trying to make generations over continuous value tokens. So one way that we do this, many of us in the audience may be familiar with diffusion. I'm going to give kind of a from 1,000 feet explanation. What diffusion does is it takes a distribution we know how to sample from, say Gaussian noise. It postulates a way to convert a distribution we don't yet know how to sample from into the distribution we know how to sample from. And then it learns how to reverse that stochastic process in order to take this distribution and sample from things we like. So that's diffusion in a nutshell. Andre might critique my explanation because he's the expert, but this is how I understand it. So when we want to do predictions over sequences, let's say we want to predict video, there are many ways that we can think about doing diffusion prediction over sequences of data. One of the maybe simplest ones is just to treat your entire sequence as sort of one data point, right? So you concatenate all the frames in your video together, and you use diffusion to predict all the frames in sequence. We call this full sequence diffusion. Another way is to do this kind of the way that next token prediction would work in a language model. We call this autoregressive diffusion or teacher forcing. There was a great talk on teacher forcing earlier this week, where what you do is you kind of make all the predictions up to some point in time, and then you predict the new token given everything from the time here. Okay? But what the kind of leader of this project, who I got to work with, but Boyan kind of realized is that there's actually a very neat interpolation between these two regimes, where rather than having to diffuse everything together as a single sequence or condition on perfectly noise-free paths, what you can do is you can just kind of have different noise levels for different time steps, and you can train a model that knows how to predict the next token given different varying noise associated with each token in the past, right? Diffusion allows you to do this. And importantly, the model gets to know what the noise level is associated with each token. So you're not dumping in noisy data and clean data into a vat. You just tell the model, okay, this time t had this amount of noise, and I gave it some noise. This time t prime had this amount of noise, and so on and so forth. So the reason we do this is that it opens up a lot of new opportunities for how we might do inference, because we can, say, predict with greater uncertainty in the distribution in the future. We can condition on things that are a bit more noisy. But I'm only going to focus on sort of one advantage of this model that's related to replica noising. So we show that, yes.
Is it fair to think of this as kind of auto-regression, but rather than coordinate order and like amount of noise order? Is that sort of what you're doing?
You can think of that, yeah, you can think of it that way, that you can go auto-regressively in any path. Exactly, that's one way to think of it. Yeah, that's a great way to think of it. So one thing we find is that this method actually has much more consistent long-term video prediction. So here we compare our method on a simple example to full sequence diffusion, which has more artifacts, and teacher forcing or pure autoregression, which has kind of pretty bad artifacts or becomes kind of gibberish. And the way that we do this is we smooth things out. So when we want to predict the next token, here subscript t is the time step. Superscript 0 means zero noise. Rather than conditioning on clean tokens in the past, we condition on tokens that have been noised just a little bit, right? And you can view this as just conditioning on the clean tokens, but with noise added. And in fact, you can re-implement the method in this way. It's not exactly the same, but you can re-implement it like this. So what do we do to train the model? Like, why is this okay? Well, it's okay because we train the model in the same way. We train the model so that it's seen histories that have been given noise tokens, right? So the model's also been trained with noise tokens plus with noise tokens during training. And so what is this algorithm? This is actually just replica noising. In fact, we're just using replica noising to stabilize things, and it works really well. So this is actually an example of an explicit algorithmic modification, but one that really only makes sense when you're predicting conditional distributions, one that only makes sense when you're working with generative models rather than mean models. You may have seen on Twitter this doom prediction video where you see somebody, predicting doom. If you read the paper very closely, I have 100% certainty that they did not read any of the theory papers we wrote, but nevertheless, you see that they actually adopt the same kind of noising trick to get this to work, as well as massively overfitting on doom data on a single level. So replica noising plus overfitting seems to work very well. Please don't shout at me, authors of this. It's a great work. The last thing I'm going to finish with is this sort of robot work. So what we do here is actually very simple. We figure out a very simple way to implement sort of regular policy, gradient policy optimization in diffusion models, and we call it diffusion policy optimization. The method is actually not particularly surprising. I'm not going to spend much time thinking about it. I'm talking about the method. I'm going to sort of talk about one surprise that I saw from how well this thing works. So on the left, what you see is oh shit, here, let me do this, right? On the left, what you see is the train policy that's trained with a diffusion model, and it's kind of like nice and smooth. On the right, what you see is what happens when you train sort of a mean parameterizing model, a model that parameterizes the mean of the distribution plus noise, and it's all shaky and erratic, okay? And you might say, okay, Max, well, this is cheating. You gave me a big diffusion model and you trained it, and it's a more expressive model, and it can probably just fit the data better, right? And you're comparing it to like a dinky little MLP. This is unfair, right? This is terribly unfair. But actually, it's a little bit more subtle than this. So the way we train these is we train them purely in simulation, and we deploy them zero shot on real robotic hardware. And if you look at the performance in simulation, the diffusion model is actually slightly worse, within a margin of error compared to the Gaussian model, right? So it's not really the case that in the distribution of the data, or in the data that these models are actually being trained on, that they're interacting with, diffusion has any advantages. In fact, in many cases, it has disadvantages because a larger model takes longer to train and explore with in reinforcement learning contexts. But what you can see is that when the model is deployed in real hardware, the diffusion model does, degrades in performance slightly. If it didn't, we'd probably be shocked. But the Gaussian model kind of falls flat on its face. It doesn't do very well. So really, this is an example not of an algorithmic modification, but somehow of richer models having sort of better intrinsic OOD inductive biases, right? That because they can kind of interpolate the data in very different ways than point predicting models, they also perform better out of distribution. And of course, we tried many tricks to make the Gaussian more competitive, and they all fell flat on their face. Just to conclude, there's one last thing that we saw in this work that was somewhat surprising to us, and it comes from how the models actually perform their exploration. So what we did is we set up a toy task, where the robot has to reach the green line by avoiding all the obstacles. And what we looked at is how the different policies are adding noise in order to explore their environments. So what you can see with the Gaussian policy is it kind of looks chaotic. It's just adding Gaussian noise everywhere. What you can see with the diffusion policy is it's sort of fattening out the coverage bands around the policy, right? It's like kind of taking the data manifold in some way, and it's kind of spreading out along what you might think of as a data manifold, or exploring in a semantic way. And this kind of geometry-aware exploration is something that's quite exciting, because it means that once we are able to train large models that might have some intrinsic intuitions, it's not simply that they might fit data better, but they might also be able to perform exploration better too, and we can leverage sort of models priors to do smarter exploration. And it seems that kind of richer models, like generative models, are able to maybe leverage this in a correct way that, say, mean parameterized models might not be. Okay, so open question, richer models, more reasonable exploration. I'm going to end with just 3 pontificating points and then let you go. The first is that there are a lot of exciting questions in continuous token prediction. I think there are some salient differences between the continuous tokens and discrete tokens. Robots, video, climate, AI for science, all these nice things. The second thing is that more expressive algorithms, more expressive models, but also intentional algorithmic choices, they can lead to richer out-of-distribution inductive biases. It's not just about being able to fit our data better or fitting more complicated data. It's also about being able to extrapolate to new data in more interesting ways. And I think the thing I'm very excited about right now, more sort of in a reinforcement learning direction, is how we can take advantage of large or very rich kind of generative models to do better exploration. So and this should also be true in LLMs for the people that don't like robots. That there should be some way to do this in LLMs as well. So these are some of the papers that we talked about. The paper highlighted in red is kind of the one that sort of theory came from. Shout out to Alan Wren on diffusion policy optimization for making something that really impressed me in terms of its hardware performance. Also my last author paper, which is exciting. And then finally, diffusion forcing, which Boyan Chen at MIT is an absolute creative genius. And I think there are a lot of cool things coming out of this work. And of course, Adam Block is also brilliant in his kind of really deep empirical study of butterfly effects in behavior cloning really informed my thinking. So enjoy your weekend. Thank you all. Thank you to all the organizers. Thank you to Andre for putting on such an amazing workshop, and have a good weekend.
Maybe before the weekend ends, there might be a
Questions, yeah.
I have a question for the relation between the diffusion forcing part
Yeah.
and the replica stuff you mentioned.
Yes.
Yeah, I just don't understand what is the actual connection.
Oh, sure. Yeah, no, I'm sorry. This is the new part of talk, so I did a bad job of adding that. So all that's really happening is when we do our inference time, right, we're predicting condition on the noisy tokens, which is equivalent to taking our clean data from the past and adding noise to it, right? So this is like the smooth policy. But similarly, at training time, the model that we've learned is also learned how to take in conditional tokens, which correspond to noisy tokens, which correspond to tokens plus noise. So you can think of this training step as kind of step 2 in the replica noising algorithm, when you train on noisy data, because diffusion forcing is trained based on historical data of different noise levels, and it's given the noise level as a sort of encoding token. So it's trained on noisy data, and then its inference is also done by adding noise to the data. And so this is kind of this corresponds to replica noising.
In standard diffusion, we also have that, right?
No, so standard diffusion, the noise is being added to the thing that you generate, right? So this is all being noise added to what you condition on, whereas in standard diffusion, we're adding noise to the object that we're generating. I think that's the important subtlety, right? So in diffusion, we're always noising things. Yes? Oh.
Following up on this question, maybe stepping back a little bit, can you explain maybe a little bit more the distinction between the perspective you're bringing with replica noising and a traditionalist perspective on doing regularization during training by data augmentation by adding noise to my data?
I think so. The difference is that okay, so there are many ways to add noise to the data. It depends which one we do. So one way would be to add noise in control. Often you might add noise to the outputs, which is not regular noising. Noising. You'd be. Oh wait, let me. Okay, adding noise to the outputs would not correspond to this and wouldn't buy you much. Now you can add noise to the inputs, which is one of the classical ways that you do data augmentation. If you do this with a mean parameterized model, then essentially what it's doing is it's like learning to smooth, right? It's kind of learning some kind of like expectation over a ball and learning to predict a conditional. But this won't give you this nice replica property because you won't actually be predicting distributions, right? You'll be predicting some biased direction that might be smooth, kind of metrically smooth, but as we saw from the counter examples, just being smooth is not enough to get away from bad inductive biases. Being smooth can still compound with the dynamics to lead to kind of negative things. The third thing you could do is you could add noise to your training data, but use a diffusion model. But the problem with this is that then most of your training data would be noisy, and if you never add noise at inference time, this would be out of distribution. The last thing you can do is precisely replica smoothing, where you do both together. And naively, you could think of all this is doing is smoothing things out, but it does so in a way that's sort of distributionally unbiased, which is maybe not so important in one-step prediction problems, but in multi-step prediction problems becomes incredibly salient because it preserves the distribution of the trajectory each time, so it avoids the compounding error, if that's helpful. Yeah.
What did K0 here?
Sorry?
What did K0?
K0 is a small kind of hand-tuned amount of noise. It's in the paper, but it's some small amount of noise that we use. Yeah. Yeah. Yes.
Yeah. So I think this one thing that reminds me is like this technical story of almost driving, right? It's like that was initially when we realized like things go out of distribution with continuous control, and I think that the solution is like you add additional camera in front of the car. Like have you heard of that story? Like 2 additional cameras so that you actually get views of what would happen when you go out of the distribution, and that so it definitely like feels similar to that story. So, but in that story, I think the thing is that when at decoding time, you don't add that noise back, right? So you just learn the policy and just decode it. Have you actually tried ablation where you don't?
Yeah, so it depends on the application. So in the standard diffusion, say behavior cloning pipeline, you are not adding any noise, and it's actually working out of the box without behavior cloning. You still need to provide sort of failure examples and teach the model how to recover. And so we're actively exploring why that still works without adding noise.
I guess my feeling is, if I try to explain this in simple form, is like I say, just take that example where the expert trajectory is just all zeros, right? And we don't have any out of distribution data. So one way you can think about it is just like, let's just perturb the state. And we know that the system is stable, which contracted and so on. So maybe in those adjacent states, just take the same action as in the expert trajectory is not too bad. So let's just do that to make sure that
so this is
we're not taking crazy actions. So, but based on that intuition doesn't tell you that you should add noise during inference time.
That intuition doesn't tell you that you should add noise during inference time, but that intuition probably works best when you have a mean parameterized policy. Because essentially what you're doing is you're just kind of learning some function and you're kind of learning it everywhere. There also will be issues where, so for example, if you're doing this from pixels, we tried this out in experiments. If you just do data augmentation from pixels with the same labels, which actually is precisely what we're doing in contractive systems, right? You can actually just think of this as data augmentation. What you find is that if you have things from pixels, pixels actually do lie on low dimensional manifolds because they come from sort of geometric, like rigid body transformations of actual objects. And then things actually don't work well if you don't add at inference time because things truly are out of distribution. Because you're used to seeing some measure that's supported on all of RD, and then you're training on some slice of RD, and then things don't work super well. So you can run into these issues. In practice, though, when you do behavior cloning with the diffusion model, they don't add any noise, and this seems to work well. It's also unclear how you might do this from pixel observations in a kind of scalable way, because it's not clear that Gaussian noising is a reasonable distribution for pixels. But what we do in the diffusion forcing paper is we add noise not directly to pixels, but to latents. And this seems to be absolutely crucial. So I think the difference is that in robotic behavior cloning, oftentimes you can kind of segment it into small tasks. But if you're doing really long horizon rich video prediction, it does seem like this form of noising and smoothing ends up being quite essential. And we have ablations where we took away the noising from diffusion forcing, and things really do go to crap. Yes?
Do you assume here that the dynamics is known?
In this case, no knowledge of the dynamics. It's pure behavior cloning. If the dynamics are known, then you can reduce to the contractive case.
Here was my question. So there was this famous conjecture in adaptive control by Steve Morse in 1980. Suppose my system is like this: xt plus 1 is xt plus a times ut, where a is either plus or minus 1, but you don't know whether it's plus or minus.
Okay.
If you know, I mean, so you could multiply it by some unknown control gain.
Yes.
And he conjectured that not knowing the sign of control gain, you're opposed. But that was disproved. There was first a mathematician who constructed this really weird-looking policy, and then two control theorists said basically, no, you just you take longer and longer intervals, like exponentially growing, and you try plus or minus.
Yes.
alternating.
Yes. So
And so here, like,
Yes.
would you do something like this?
Aha.
Maybe,
that's a great, yeah. So we thought about this. So to be perfectly precise, this lower bound from this other forthcoming paper, we have to restrict our policies to things that are not time dependent and things which are to smooth. So the reason for the non-time dependence is actually kind of the really salient point, because essentially we need to say that our policy cannot be allowed to do adaptive control. Because indeed, if a policy can do adaptive control, it can learn the dynamics, it can fix all this. So you can't let your policy be an online learner.
Right.
So in fact, the lower bound restricts to what we call, so if the system is non-contractive, then we have a lower bound against arbitrary policies. And that's a pretty easy argument. But for the argument against stable systems, yes, we need to restrict the power of it. So for example, in context stabilization, or whatever you'd want to call that, potentially will offer more power. Yeah, that's a great point. We actually don't know how to have lower bounds against adaptive policies. Probably none exist. And I can even show you the construction for the lower bound and show you how you get around it.
That construction is just pure, great example of exploitation, exploration.
Yeah.
The thing is, you never have to learn a sign. You just keep alternating.
So one thing that we try to do, so that the smoothness construction, I'll let everybody go in a second, but I'll just tell you real quick. The smoothness construction we do, just to keep things simple, we do it by sort of embedding kind of a particularly nasty two-dimensional linear system. If we could take that 2D linear system and show that there's like a d-dimensional variant, then you could probably show that the adaptive control would take something like 2 to the d, and that would just come into your lower bound. The problem is that we haven't been able to, or we haven't had the patience or the stamina to try to extend the system to a really pathological d-dimensional one while ensuring all the conditioning and all the other properties and Lipschitzness properties don't get blown up as well. But we should talk more offline about this.
Okay, I think we're just going to close now and we can talk offline.
Cool.
Yeah.
Sounds great.
Let's thank the speaker.
Thank you.
Thanks, Andre.